Hi, my name is Burak, and I will be presenting our work titled HTTP Adaptive Streaming over Multiple Network Interfaces. My co-authors are Sarp Öztürk and Ali Cengiz Ben from Özyeğin University as well. Sarp and I, we are both senior computer science students, and this work is also our senior design project. Professor Ben is our project supervisor. Today, I will be briefly talking about our motivation and goal, then the example scenario, our approach and implementation. Then I will conclude with a list of things to do for future work. So let's start with our motivation. Today, internet users in rural areas are experiencing unreliable network connections and low speeds in their DSL services. Even in urban neighborhoods, users might experience the same problems if they are far away from DSLM or the central office. In such cases, when the users want to stream online videos, problems like low quality video and frame freezes are inevitable. In live streaming, the latency will likely be high, or video might freeze quite frequently. All these lead to poor user experiences, and the users might stop using and paying for streaming services. Getting a secondary network connection might help in many cases in terms of increasing the bandwidth available for the user. In particular, it might help with the browsing scenario. It's an existing technology known with names like link aggregation and broadband bonding. The in-home clients connect to a gateway that has two outgoing connections to the same or different ISPs. When we talk about streaming, getting a secondary connection might help, but to achieve its true potential, we need to use multiple connections in a smart way. Otherwise, the user may not see the improvements he expected. So, the smart way I just mentioned refers to making the gateway streaming aware. If we put the intelligence in the gateway, there is actually no need to add or change anything in the clients or the streaming applications themselves. This makes this approach much easier to deploy, and note that some of the platforms would not allow us to make the necessary changes in the applications running on them. So, if we assume that the gateway is programmable, this is the cleanest approach to go. Once the updated gateway is in place, any client and application can benefit from it, meaning that they can watch better quality streams with a lower latency. I will mention the details of our solution in the next couple of slides, but before moving on, with our solution, service providers and content creators can reach a wider user base. In other words, they can sell their products and services to more people now who would not be eligible before. Our goal is to improve user experience in streaming applications. We want to achieve this goal by ensuring less stalling, that is freezing, higher video quality and lower latency for live streams. How we want to accomplish that is using multiple network connections simultaneously, considering their bandwidths or delays, or cost per byte and data cap for each connection. There are a couple of real-life scenarios that users might have. For instance, users may have to slow no-cap DSL connection. In this case, they can use both network connections effectively thanks to the smart gateway. Or as another example, users might have a slow no-cap DSL connection and a fast but capped and costly LTE connection. Using LTE is nice as it might provide much faster speeds than DSL, but one may run out of his data cap very quickly. So it has to be used carefully. In the next slide, I will talk over this scenario and how our solution is implemented in a case like this. Here we have an example scenario which demonstrates the project clearly. We have a client, the smart gateway, and the media source. As we mentioned, our solution focuses on the gateway part. Note that the gateway has two external networks. One of them is a slow DSL connection and the other one is an LTE connection. LTE is faster than DSL, but what we want to minimize the waste of LTE connection quota and improve the streaming experience compared to the session with a single slow connection. For this purpose, the gateway is designed as it learns the states of each network and keeps the state information during all process. It actively measures the bandwidth of each network by sending HTTP head requests to the media source at the beginning. It continues with passive measurements later on during process. We consider HTTP adaptive streaming, and first the client sends a request for a media segment over the smart gateway like it would normally do. The gateway parses this request. It assigns loads to each network according to a number of factors including the bandwidth. The gateway then splits the request using byte range. If there is only a single network available or the gateway decides to use only one network, it does not modify the outgoing requests. Once the sub-responses are received from the media source, the gateway merges them and forwards this merged response back to the client. As a recap, our approach is transparent to the clients as well as streaming applications. The complexity is in the gateway and it's trusted by the clients. It runs the split and merge strategy. Also, the smart gateway is adaptive to the network changes and it has cost-aware load distribution capabilities. A user or the ISP itself can set minimum or maximum usage ratios for each connection. Moreover, the smart gateway adapts itself to changes using bandwidths and delay data for each network, meaning that when a problem occurs while fetching a requested object, it can retry fetching it using the other connection. In our experiments, we observed that the largest benefit was achieved when two similar networks were used in case of no data capping, like two slow DSL connections. If one network was capped but also fast, like LTE, it still helped reducing the stalls as we used the LTE in emergency situations, like when the buffered data was at a critical level. To briefly talk about the implementation, almost all development was completed in Python. Python has a wide number of libraries that are useful for this kind of purpose. Since this development was also a part of our senior design project, further scale testing is needed for more accuracy. Also, we considered only non-secure HTTP traffic, but the gateway's certificate can also be installed and trusted by the clients. Thanks to this solution, many more users can qualify for higher quality streams like HD or 4K, meaning that telcos and mobile service providers can bundle their services and benefits from idle LTE capacity. You can download and use our code from following GitHub link or by just scanning the QR code. Also, you can improve our code if you desire to. We would be glad to work on issues and bugs. You can reach out any of us by following emails. Thank you for your attention and interest in our work.